Welcome back. We would like now to learn how we react to solutions together, and the process of putting the solutions together so that they can react is called titrations. And already we have prepared two solutions. Remember the other lesson, we prepared a solution of oxalic acid 0.25 m, and we have a solution of sodium hydroxide. This solution, its concentration is unknown. We are going to react those two solutions, and the process of reacting them will involve putting one solution in a conical flask. This is a conical flask, and we are going to place sodium hydroxide here. Then we will put an indicator. The purpose of the indicator here is to check for us when the reaction has come to an end so that we can stop the reaction. The process that we call titration, when the reaction is over, the indicator changes and we say that the titration has come to an end point, and we stop reacting. Then we take the data and we start our calculations. In this process again, we will use a burette, and the burette is calibrated from the top, 0 mark, all the way up to bottom. We have 50 mils and 50 centimeters cubed. So if you fill the burette up to 0 mark at the top, the solution that you can be able, the maximum amount of solution you can be able to run out is 50 centimeters cubed. So we want to react those two solutions, and the objective of this titration will be to determine the concentration of this solution. The process of determining the concentration of an unknown solution is called standardization. You are standardizing. We are going to standardize the solution of sodium hydroxide. We are going to look for its concentration, and we already know the concentration of the other solution. So that is the objective of this practical. Remember, oxalic acid, its RFM is 126, and the formula is H2C2O4. It has got 2 water of crystallization. Now, the other type of titration that we are going to do in the future is redox titration. Redox titration does not require an indicator. For example, in this titration between oxalic acid and sodium hydroxide, we are going to use a phenolphthalein indicator, and we will know when the reaction between the two substances will come to an end. During the titration, we need to know the volume of sodium hydroxide we have placed in this conical flask. Therefore, we are going to use a pipette. This is called pipette, and pipette has got its capacity, and we have different types of pipettes. Some have a capacity of 20 mils, others 10 mils, others 25 mils, and so on. The pipette that we are going to use has got a capacity of 25 mil. So what we are going to do in this practical, we are going to suck up 25 mil, and when it reaches this mark, that mark indicates that the solution inside is 25 milliliter. So we will place that solution inside this conical flask. Then after that, we are going to add this indicator. This indicator will make the solution to look pink. It is called phenolphthalein indicator. And then we are going to react the two solutions here. When the other solution runs down from this burette, then runs down there, when the reaction is over, we will be able to see that it is over. And let us now titrate the solution of oxalic acid we prepared. This is a solution that we prepared of oxalic acid. It is 0.25 m. This solution is of sodium hydroxide, and this solution, its concentration is unknown. We want to standardize it, or in other words, we want to know its concentration. So let us go. The first step is we are going to put the solution of sodium hydroxide here, and then we put phenolphthalein indicator. Right now, I don't want to use the pipette filler, so I'm going to suck it up. I put it in this flask. Adjust the solution up to the 25 milliliter mark. Adjust it to 25 milliliter mark. Now I have my solution at the mark of 25 milliliter, and as you can see now, we are having 25 milliliter of sodium hydroxide. Let us now put the solution into the conical flask, and it seems that it had some impurities of the indicator, but there is no problem. We are going still to do our practical. We have 25 centimeters cubed of sodium hydroxide whose concentration is unknown. Let us now put the indicator. This is a phenolphthalein indicator. We want to get a few drops, 4 drops of phenolphthalein indicator. And 1, 2, 3, 4. We have our indicator. Phenolphthalein indicator changes all basic solutions, all alkaline solutions, to pink, and that's why our sodium hydroxide is turning pink. Let us now put oxalic acid into the burette. Let us close the burette there. Let us adjust our solution to any point we want. Our solution now, we have adjusted it to read 5 centimeters cubed. So our burette reading is exactly 5 centimeters cubed. I would like now to react the two solutions, as I had told you that we want to react the two. So let us now titrate. Open with your left hand, open the tap with your left hand side, and then you run the oxalic acid into the conical flask. You start titrating. This process is called titration, the process of reacting the two solutions together by pouring one solution into another one. So this is a titration process. Continue adding slowly by slowly, don't add a lot. And as you observe, my solution is almost turning. It is supposed to turn colorless at the end point. Now is colorless. It has turned from pink to colorless. This indicator, we call it phenolphthalein indicator. It is normally colorless in acids. Therefore, we have reached our end point. And you have to note that end point is characterized by a change from, like now, pink, very sharp, to colorless. Let us now read the final burette reading so that we can do our calculations. The final burette reading is exactly 25 mils of sodium hydroxide solution. Those values we have obtained, the value we have obtained from our burette can now enable us to do calculations to determine the concentration of this sodium hydroxide solution, and that will be our next step. Two solutions of oxalic acid and sodium hydroxide, and what we have, the result we have now is that the result we have is the solution of sodium hydroxide. Its concentration is unknown. Then we have the other solution of oxalic acid. The concentration is known. The concentration is known, and it is 0.25 m. As I had told you earlier, the aspect of a solution, the data about a solution is only two, its concentration and its volume. So we have oxalic acid. Let us represent it as H2X, and that is H2X, and the other one I want to represent it as sodium hydroxide in form of a formula. Sodium hydroxide is monovalent and oxalic acid is a diabasic acid. And the volume here we have titrated, we have found it is 25 minus 20, which is equal to 20 centimeters cubed. This other volume, remember, it's the one that we pipetted using 25 ml pipette, and the volume was 25 centimeters cubed. The concentration of sodium hydroxide was unknown, while the concentration of the oxalic acid was 0.25 m. To standardize the solution is simply to find its concentration. So we want to find the concentration of sodium hydroxide. To do that, we need first to work out from this volume here of oxalic acid and the volume of and the concentration of oxalic acid, we can be able to calculate the number of moles which were run out of the burette. So moles of oxalic acid. From the previous lesson, we said that if I want to calculate these moles, I will calculate it like this. From previous lessons, we said that to calculate moles in a solution, we get the volume, and the volume here is 20. You divide by 1,000, you multiply by the molarity, which is 0.25, and that now, those now becomes the moles of oxalic acid, which are 20 multiplied by 0.25, then divide by 1,000, and we get the number of moles here are 0.005 moles of oxalic acid. For the sake of writing chemical equation, let me represent oxalic acid as H2X because it has got two replaceable hydrogens. And then let us write the equation. In this case, to calculate, because the second step here is to calculate the number of moles of sodium hydroxide using the number of moles of oxalic acid. And to do that, we need to write a chemical equation. A chemical equation between oxalic acid and sodium hydroxide, so that you can get the mole ratio, the particles ratio. Therefore, we have H2X plus sodium hydroxide. We get Na2X, which is a solution, plus H2O. Let us balance this chemical equation. Sodium hydroxide are 2, so we multiply sodium hydroxide by 2. Then the number of hydrogens on the left are 2, and 2 plus 2. There are 2 hydrogen in H2X and 2 hydrogen in sodium hydroxide. Those ones are 4, so we multiply water on the right hand side by 2. The mole ratio now from our chemical equation is 1:1:2. But our interest is the ratio between H2X, that is oxalic acid, and sodium hydroxide. So they react in the ratio of 1:2. That is, we need double the number of sodium hydroxide particles as those ones of oxalic acid. And already we have calculated the number of moles of oxalic acid. So the number of moles of sodium hydroxide must be double. That's what we can see from the chemical equation. Therefore, moles of sodium hydroxide which have been reacted, and remember these moles were in the conical flask, and those moles were in 25 centimeters cubed, because remember we pipetted, our pipette was 25 centimeters cubed. Those moles now are 0.005 multiplied by 2, because we need double the number of particles of sodium hydroxide as those ones of oxalic acid. These are the moles, and the number of moles here becomes 0.01 mole. So those are the moles we had in our conical flask, or those which were neutralized by oxalic acid. Now we want the concentration. How do we calculate the concentration? It's now very easy, because we are going to extrapolate. We are going to move from this idea that we have 0.02 moles, and we have 0.01 moles, and they are in the conical flask, which and they are in 25 centimeters cubed. So it's just extrapolation. Our concentration is based on per liter, but here we find that the number of moles we are getting, they are in 25 centimeters cubed. Therefore we will extrapolate from there. How are we going to do it? We are going to say that in 25 centimeters cubed we have discovered that there are 0.01 mole of sodium hydroxide, and we want now to find out 1,000 centimeters cubed of such solution. How many moles do you find there? And as I had told you earlier, that we could concentration in terms of how many moles are there in a liter. So this is 1,000 over, that is centimeters cubed, over 25 centimeters cubed, multiplied by 0.01, and the concentration now becomes centimeter cube, and centimeter cube cancels, so this becomes 10 divided by 25, and the number of moles now become 0.4 m, and this is the number of moles per liter, which we write it as 0.4. So now we have standardized the solution of sodium hydroxide. Therefore this solution here is now 0.4 m.